So we move on to correlation and regression analysis from analysis of variance. It's a different but related topic. So we'll cover what the difference is between the two, correlation versus regression. We develop what the Pearson correlation coefficient is. This is R. And if you square that value, you get the variance explained. So I'll show you how these two are related. And last but not least, we talk about correlation versus causation. Because that's sometimes what you're after. So if you're looking at two variables and you're looking at associations between the two, the reason for the analysis is often that you want to figure out if one factor causes another one. The use case for correlation and regression analysis as opposed to analysis of variance is that your predictor variable is a continuous variable. So it's not a class variable like variety A, B, C that we had in our examples, but it is a continuous predictor variable. And the difference between correlation and regression analysis is primarily driven by the question you're asking. So if you're asking, is there a relationship between a predictor and a response variable, then that's a correlation analysis. And if you're using an equation to predict one variable from another, that's a regression analysis. So the math behind the two is actually identical, but you're simply using different aspects of this analysis. So Pearson correlation coefficients, that is usually abbreviated by R. That coefficient describes the strength and direction of the relationship. And if I just visualize this in these plots here, they range from 1 to -1. So if I have a perfect correlation between x and y, that is a value of +1. If there's some scatter, some residual variation, then it's a value between 0 and 1. If there's no relation whatsoever, then my correlation coefficient is 0. And if my correlation is negative, so with an increasing x value, I have a decreasing y value, that is indicated by a negative sign for my correlation coefficient. And that relationship can also be described by a linear regression equation, and you're probably familiar with this. So I can describe this relationship with a line, and the equation for this line would be the predicted y value, so that would be that line here, is an intercept, so that would be this value, plus my x value multiplied by some sort of scaling factor, and that is the slope. So if I go 1 unit to the right, I would go b units up, or in case of a negative relationship, my b value would be negative. So in that case, I would go -b down to arrive at my y value from an x value. And so the way the correlation coefficient is calculated is actually from this equation, but with standardized data. So if you standardize both your x and your y variables, so you subtract the mean and divide by the standard deviation, then my slope is the Pearson correlation coefficient. And therefore you can also say an increase of 1 standard deviation in x leads to an increase in r standard deviations in y. So r is that slope if both x and y data is not in original units but expressed as standard deviations from the mean. And that Pearson correlation coefficient is also related to the proportion of the variance explained. So that's the R² value. And that is a variance in y explained by x through that regression equation. And you can visualize it like this. So if you have a y and an x variable and you do a scatter plot of this, you can also think of the variance in y in isolation. So if I were to draw this on here, that y value has a distribution and has a variance, right? So it has a mean, that's that value right there. And I can calculate what that variance y is, right? So those are the sums of squares that describe the deviation from the mean of y. And if I fit a regression equation to those points, I can also do the same thing that we've done before in ANOVA. I can calculate the residual values, right? So the deviations from the regression equation, that is my residual error. And then the variance explained, that is actually the difference between the regression line and the mean of y. So I indicated those in different colors here, and you can put them all on one graph if you want, and they all add up. So you can now calculate proportions. So the r square value is actually the variance explained divided by the total variance in y. So it's a proportion of the variance explained, the green ones, over the total variance in y. And that's actually also a signal-to-noise ratio. You could have a different signal-to-noise ratio, so you could put the residual here, so the red ones. But that is not what is being used in this particular case. So my noise in quotation marks would be the total variance, and that makes r or r square also a test statistics. So you can ask, what's the probability of getting that kind of signal to noise ratio just by random chance? And so there are tables that you can look up, in fact, that and one is included in the lab, that simply tell you for an r value and a given degree of freedom. So your degree of freedom is always n-1. So if you have 4 points, it would be 3, because the mean of y is used in this calculation. Then you can look up whether that is a significant association between x and y. So p-value flows directly from r as a test statistic, or r squared, so it doesn't really matter. You can use either one. So also correlation and regression analysis has some important assumptions and caveats. So normality is one of them, and just like in analysis of variance, your dependent variable has to be normally distributed for a given predictor variable. So in analysis of variance, your predictor variable is actually fixed. So either it's a continuous variable that you only investigate at certain levels, or it's a class variable that has an effect on your dependent variable. So conceptually, that's exactly the same assumption here. So my residuals have to be normal after the effect of x has been accounted for. So you can actually use the exact same syntax in R to do a residual plot and investigate your assumption of normality. Now, there's another interesting assumption in correlation analysis, and that is how your x variable is distributed. If you're asking the question if your predictor variable x and your response variable y are significantly associated, then also your x variable has to be normally distributed. Now, if you're after a regression, so if you actually just want to predict y from your x variable, then that's not a problem at all. So x does not have to be normally distributed. In fact, most of the time you do targeted sampling in regular intervals. If you simply want to predict y value from an x value, x does not have to be normally distributed. And the reason for this assumption is that the distribution and range of your x variable really drives the r square and r value, and therefore also the significance of the association, right? So if you investigate the full range of your x values, you might get a high correlation coefficient. But if you actually just cut out a portion of that section here, and you plot exactly the same values, you can already see it here that my correlation would not nearly be as strong. So your correlation coefficient drops and your significance value drops if you restrict the range. So that's an important consideration that you have to keep in mind. And that makes the Pearson correlation coefficient also a really poor statistic for cross-study comparisons. So one person may investigate one range of values, another person another range of values, a wider range or a different range. So those can very, very easily yield very different r and r square values. So unless you have a really representative random sample of your population, every study would come up with a different answer. And another important caveat here is that correlation and causation are actually two different things. So that applies both to correlation and regression analysis and the inferences and predictions that you make. There's actually a rather fun and interesting example out there. I think there's some database, I think it was done in one European country, where they just looked at large databases of health data, economic data, census data. And so one of the strongest associations that they found was the relationship between drowning death and ice cream consumption. That was a correlation of 0.9 or something like that. So a very strong association between those two variables. And you could ask, is this ice cream consumption causing drowning death? If people eat too much ice cream and then they go swimming, then they sink. What is going on, right? And the answer is, of course, while there is a strong correlation, there is no causation here, right? So what happens is that a third variable influences both of those factors. So if you have a hot summer day, then people eat lots of ice cream, and they also go swimming. And because lots of people go swimming, there'll be more drowning deaths than on a rainy day where people stay at home and don't eat ice cream and don't jump into the lake either. So these things are actually very common. You have to watch this. So somebody actually, inspired by this example, they actually dredged a database in Maine for statistical census data, and they could also find a strong relationship between ice cream sales and forest fire. So it's a replicable result. It's really awesome. But if you plot it over time, you see that this is driven by hot summer temperature that both in August boosts the ice cream sales and the forest fires. Or here's another one they found that's just as good. So that's in fact a negative relationship. So the more ice cream you eat, the less weight you gain. So that is the same effect here. So obviously in the summer people are more active and lose weight, and at the same time that's also the time where you have ice cream consumption. But it doesn't mean that ice cream consumption is a good strategy to reduce your weight. So that's always something you have to keep in mind when you do correlation and regression analysis. The correlation itself does not necessarily mean that there is a causation. There is probably some causation going on, but it may not be between the variables that you're looking at the moment. And very often you look at matrices of predictor and response variables, and all kinds of correlations are possible, right? So I could look at forest fire over temperature or ice cream sales over temperature, and this would give me sensible correlations. But forest fire over ice cream sales, that doesn't work. Weight over ice cream sales doesn't work. I could try forest fire as a function of weight. So, if people gain weight, does this cause forest fires? So if you have a large data set, there's quite a number of correlations that you get. Usually a small amount are actually causal relationships. And most of the time, those relationships just mean that something else influences both. So that's called collinearity if you have multiple variables that are related to each other. And there is actually no analytical silver bullet to disentangle collinearity, really. So that is a serious problem in any kind of multi-factor analysis, risk factor analysis, and medical research. So if you observe people having heart attack or cancer and you throw all kinds of environmental and lifestyle variables at it, what is really the cause of what is sometimes very difficult to figure out. And there are advanced analyses that help you a little bit with this. So path analysis is one of them. It's a form of structural equation modeling. There are also approaches where you look at whether a correlation still holds up after you account for another potential predictor variable. But these are really all not real solutions. So in this particular case, if I wanted to test whether it's temperature or time of the year that causes forest fire, or whether ice cream sales may also cause forest fire, so you could account for ice cream sales and see if then there's still a residual effect of temperature on forest fire. And what you may get is that normally temperature explains 80% of the variance in forest fire. And after I account for ice cream sales, then temperature still accounts for 20%. So that may be your result, that temperature accounts for 20% of the variance in forest fire. And that's a nice and advanced analysis. But that really doesn't make sense because temperature is really the driver, right? So you have to use your common sense and just dismiss certain factors where there's just no plausible relationship possible. And so those cause and effect relationships and their strength and their importance cannot be revealed by any kind of analysis. So this is something it's a confounding factor. So once you have confounding effects, this is an unsolvable problem. So the only real way to get to the bottom of this is actually to experimentally verify these things, right? So you would have to hold one factor constant in an experiment and vary the other. And of course that you can do in many situations, but not always. So sometimes you're stuck with just using common sense, and structural equation modeling can help you a little bit as well. We'll cover this in another course if you're interested in these kind of things. It's a little bit more complicated. And it's certainly also no silver bullet to disentangle collinearity. So if you're just looking at simple matrices of correlations, look for the highest ones and apply common sense in interpreting this. This is actually your best bet to create some insight.